In this video, I'm going to do one example of curve sketching. In this particular one, I am going to be doing a rational function. I am going to assume that if you are at the point where you need an example of curve sketching, that you already know how to calculate your first derivative, your second derivative, things of those nature. So I'm not going to work out the calculations for the first and second derivative because we're going to focus mainly just on the curve sketching. Alright, now there's going to be a bunch of things that you're going to want to do. I have my students find certain things first before we start really delving into the calculus of things, because you can find out a lot about this function just from your pre-calculus knowledge. Alright, so usually the first thing, if I've got some function and I want my students to calculate curve sketching, then I tell them, okay, start with your x and y intercepts because those are really easy to find. Okay, so let's do that on this one here. Alright, let's say we're going to find our x-intercepts. Alright, which means we're going to set y equal to 0. Alright, so we'll go ahead and do that. We're going to have a 2x squared minus 9 all over that x squared minus 4. And we're going to set that equal to 0 so we can find those x-intercepts. Multiplying both sides by the x squared minus 4. Okay, then that'll leave us with the 2x squared minus 9 equals 0. I can divide both sides by that 2. Then I'll have the x squared minus 9 equals 0. Add 9 to both sides. And I'm going to get an x equals a plus or minus 3. Alright, so then I know I've got plus or minus 3, 0 for some x-intercepts there. Okay? And then I have them then calculate your y-intercepts. Alright, we know that plugging those, for y-intercepts, plugging in 0 for x. So then I'm going to have a y equals 2, 0 minus 9, all over a 0 minus 4. Doing a little bit of math there, we're going to have y equals a negative 18 on top and a negative 4. So y equals about 4.5. So then at 0, 4.5, we'll have our y-intercept. Alright, so those are two things that we can really quickly put on our graph. Okay, then I usually have my students look at some horizontal and vertical asymptotes. Alright, so here, let's box this problem out so it stays separate from our work. Alright, so then looking at our vertical asymptotes, since it is a rational function, then we know we need to set that denominator equal to 0. So x squared minus 0, or x squared minus 4 equals 0, x squared equals 4, x equals plus or minus 2. So we've got some vertical asymptotes hanging out there at plus or minus 2. And then my students know the shortcut rules for finding the horizontal asymptotes of a rational function. If I distribute that on top, then my function is going to look like a y equals a 2x squared minus an 18 all over an x squared minus 4. And my students have memorized that when you can look at the rational function and your power in the top and the power in the bottom is the same, in which case I've got an x squared here, then my horizontal asymptote comes from those leading coefficients. So I'm going to have a horizontal asymptote at y equals 2. Okay, so we go through, we gather a bunch of this type of information. Okay, at this point then I usually have my students do first derivative. Okay, and I'm not going to take the time to calculate that first derivative just because that's going to be a quotient rule. It's going to be really, really big. So we'll just write down here our first derivative. Our first derivative here ends up as a 20x all over an x squared minus 4 squared. Alright, and if you want to calculate that derivative by hand, go ahead, hit pause, calculate that derivative, and see if you can come up with that first derivative there. After we do first derivative, then I have them find critical points, because we are going to use a number line at some point here. So it is a rational first derivative here, so we set our numerator equal to 0, and we get x equals 0 as one of our critical points, and then we set the denominator equal to 0, so x squared minus 4 quantity squared equals 0. Square both sides, add 4 to both sides, so x squared equals a 4, so I'm going to get an x equals a plus or minus 2. Alright, so then we've got some critical points. Let's go ahead and label those. we've got some critical numbers right there. And so on my number line, when I get to that point, we're going to put plus or minus 2 and 0 on that number line. All right, we do actually go ahead then and calculate that second derivative because we're going to need that in our number line to tell us and help with the concavity. And here again, it's another quotient there, so it would be quite a long derivative to work out. So I might highly suggest that you pause the video and see if you can get these first and second derivatives. But second derivative here is going to be a negative 60x squared minus 80. And then we're going to have that x squared minus 4 to the third power. Okay, and then we would set both of the numerator and denominator here equal to 0, see if we could find some possible points of inflection. Alright, looking at that numerator right there, it's going to end up being a negative underneath the square root, so there will be no critical points, or no, sorry, points of inflection there from the numerator, and this denominator here would give me the exact same plus or minus 2 for points of inflection, so I do not have any additional points that I would need to put on my number line. Okay, so what I'm going to do here is I'm going to pull in some graph paper and a little chart. So there's my graph paper, and then I've got a little chart down here. So usually at this point, my students have been making individual number lines for finding, testing first derivative and finding increasing, decreasing intervals. Then they have done a different individual number line for finding, excuse me, concavity, concave up, concave down. So usually by the time we get to something like curve sketching, then we just make one great big box. Here's my number line. I kind of make it kind of organized so that we know that we've got intervals across the top. We're testing our first derivatives. That's going to produce some relative maxes and mins. Then we take a look at our second derivative and we write our results down. That's going to result here in some points of inflection. Okay, so let's come back over here and put on the stuff that we found initially. Okay, so we said that there were x-intercepts at plus or minus 3. Okay, so I'm going to go ahead and put those on there. So at negative 3, I've got an x-intercept, and at positive 3, I've got an x-intercept. We also said that we had a y-intercept at 0, 4.5. 1, 2, 3, 4, so roughly right about in there. So get those intercepts put on there. Okay, then the next thing that we said we had some vertical asymptotes and horizontal asymptotes. So let's go ahead and put those on. Vertical asymptotes at negative 2. And another one at positive 2. Alright, and we said we had a horizontal asymptote at 2. 1, 2. So go ahead and put those things on because those are really easy, simple things that we can do. Okay, and then now we're going to start working with the calculus part of it. So we're going to take all of these critical numbers, and had there been any points of inflection, we would have done those as well. Now on ours, we line them up here with our intervals here. So I'm going to have a negative 2, I'm going to have a 0, and I'm going to have a 2 right there. Okay, so that gives me this interval would be negative infinity to negative 2. This interval would be from negative 2 to 0, 0 to 2, and then 2 to infinity. Okay? Alright, now we're going to test this first derivative. Alright, so let's go ahead and box that in so it stands out just a little bit there. Okay, so there's the first derivative, and here's the second derivative, because that's what we're going to need to be looking at to do these. Alright, so first derivative, if I plug really large negative number in here, I'm going to have a negative divided by a positive. That's going to give me a negative, which means then that original function has to be decreasing in that interval. Alright, in between 0 and negative 2, let's plug in a negative number again, like negative 1. So again, top's going to be negative, bottom's going to be positive. So again, this is negative, which makes that original function decreasing. Alright, plugging a positive 1. That numerator will remain positive, and this bottom is going to remain positive too, because it'll be negative, but when I square it, it gives me a positive there. So I have positive, which means my original function is going to be increasing now at this point. And then another big, really big positive number, again, positive in the top, positive in the bottom. So positive and increasing across the board. Okay, so then what that tells me is that when I go from decreasing to increasing right here at 0, then that has to be a minimum. Okay, so I'm going to put that on there. We need to actually find the ordered pair there. So right here, I know I have a minimum, and that ordered pair would be at 0. Now we're going to have to plug that into the original function. Let's plug in 0 here. If I plug in 0 here, I'm going to have a negative 18. Plug in 0 here, I'll have that negative 4. So that y-intercept that we calculated there at 4.5 is going to be a minimum. So I've got the ordered pair on the graph. That's going to be a minimum right there. Okay, now let's keep going. We'll fill in the rest of this chart here. Alright, now I'm going to have to take a look at the second derivative. Alright, so taking a look at the second derivative, let's move this up just a little bit there. Alright, second derivative here, if I plug in a really big negative number, that'll be positive, so this is going to remain negative. Alright, minus negative, so I'm going to have a negative on top. Plugging in, it really doesn't matter here because I squared it's going to be positive, but it's going to be really big, so I'll have a positive on the bottom. Alright, so negative over positive will be, usually on cavity I say less than 0, and when the second derivative is less than 0, then I have a concave down on my original function. Alright, plugging in a negative 1, here again, same, it's going to be the, oh wait a minute, this will be negative on top, and then plugging in a negative 1 here, negative cubed gives me another negative, so negative divided by negative, this one's going to be greater than 0. Almost missed that one, and then that makes the original function concave up. Alright, plugging in a positive 1 here will give me a negative on top. Plugging in a positive 1 here, negative cubed still going to be negative, so again, greater than 0, and a concave up on the original function. Now, a really large number. So a really large number will give me a negative on top. A really large number here is going to give me positive in here, so now I'm back to a less than 0 negative, which would be a concave down. Okay, now taking a look at this. Alright, now from concave down to concave up, when that change occurs, then we usually have a point of inflection. Alright, but this is at negative 2. Alright, well, at negative 2, I don't have a point of inflection. I've got a vertical asymptote, so I did not have any there. And then when I switch from concave up to concave down here, this is at 2, but I already know what's going on at 2. I have a vertical asymptote at 2. Alright, so I do not have a point of inflection. So there are no points of inflection on this one, so we can just put none right there. Alright, but now you're going to take the chart and you're going to finish your sketch. Alright, this lays everything out really nice and neat for you. Alright, from negative infinity all the way up to this negative 2, I've got to be decreasing. I know I have to go through this point, and I need concave down. Alright, well, so if that's an horizontal asymptote, then I got to be coming in this direction, hugging that asymptote, and coming through that point. Alright, I am concave down. Okay, and the function is decreasing. Alright, now taking a look at this interval from the, well, I could even go all the way here. Let's go all the way up to that negative 2 there. Well, yeah, let's go all the way up. Better hug against that. Alright, now from negative 2 to 0, I got to be decreasing, and I got to be concave up, and this point here has to be a minimum. So to get this being a minimum, decreasing function and concave up, I'm going to have to start all the way up here and hug this asymptote, and come down so that that ends up being a minimum right there. Alright, from 0 to 2, alright, I've got to have an increasing function with concave up. This still has to be a minimum here at 0, 4.5. Alright, so I've got to get increasing and it's got to be concave up. So I'm going to finish that right there. And then on this last interval from 2 to infinity, I've got to be increasing again. And so increasing can't be down here. Increasing is going to have to be down here. I got to be concave down. I got to go through that x-intercept right there. I've got to hug here. Alright, now let's check and see. Yes, I am increasing. It is concave down. I go through that point. Okay, so it's a matter of going through each of those little intervals and then checking to see what you've got going on there. So I definitely have a minimum. Everything is increasing, decreasing, concave up and concave down like it's supposed to be. So just, a nice example of walking through all the different parts of a curve sketching that you can do. Lots of things that you can do without any calculus whatsoever, and it's not till the very end when you calculate that first and second derivative and you look at the critical points and you look at the possible points of inflection before you actually apply some of your calculus there. So definitely thanks for watching, and be sure and subscribe to the channel. Thanks.